Hi everyone. I think we've now got everyone here, so I think we're gonna kick off. So welcome everybody to what is now our 20th Inspiration Exchange session. My name is Fergus Zimmer and I'm a postdoc in the Schaar Lab, and I'm going to be moderating today's session. As always, I'd really like to thank Tennyson Liu for his help in co-organizing these sessions together with Nahela and myself. Welcome back now after the summer break to those of you who have been to one of these sessions before. I'd just like to really welcome everybody who's joining us for the first time today. Today's topic for the session is going to be on one of probably the most significant advances in time series modeling in recent years, and that's neural differential equations. Before going any further, I want to give a big shout out that our lab is recruiting for our 2023 intake of PhD students. We have several fully funded positions available, so if you're interested, please apply using the form on our website. And to do this, you go to the vanderschaar-lab.com website, click on Join Us, and then complete the short form. In addition, we're going to be holding a recruitment meet and greet session at the end of October on October 31st. So do attend if you're interested, have questions about what a PhD in our lab would entail, or would simply just like to meet and chat with a few of the students from our lab. So without further ado, back to today's session. As always, the ongoing aim for these Inspiration Exchange sessions is to explore the breadth of topics in machine learning for healthcare and to generate ideas for future research and collaborations. To give a brief overview of today's session, after my short introduction, I'll be passing over to Zhaozhi Qian, who will give a short introduction into neural differential equations and motivate why they're important for healthcare. After this, two of the PhD students from our lab, Sam Holt and Nabeel Seedat, will give presentations on recent work that they've done using neural differential equations. We'll then move to our roundtable discussion with our industry leaders. We're delighted to be joined by two guests today, who I'll introduce more properly later in the session. And after this, we'll open up the discussion and invite everybody to ask questions of either our guests or any of our presenters from today. As usual, please post your questions in the Inspiration Exchange channel on our Slack, and the earlier is the better. If you don't have the link to the Slack, I think Tennyson will now post it in the chat, so you can access it from there. So now, without any further ado, I'm going to pass over to Zhaozhi for his tutorial on neural differential equations. Zhaozhi, please take it away when you're ready.
Hello, everyone. Thanks again for coming to do today's Inspiration Exchange. And I'm very glad to introduce a very interesting recent topic in time series, and that is neural differential equation. In today's session, we'll also be talking about, I'll be motivating what is neural differential equation, why it is important, and Sam and Nabeel later will talk about the two recent works from our lab that falls into these areas. And of course, you are also invited to read more online on our website. So healthcare time series data poses many different challenges. For one thing, the time series data has many modalities that are complex and diverse. We have data ranging from the EHR medical records to sensor data collected automatically, for example, from wearable devices. And this gives a wide range of different sampling mechanisms, from sparse to dense, regular to irregular, informative to non-informative. And typically the time series data also contains a mixture of continuous binary categorical types. The prediction task and outcome of interest can range from rolling dynamic prediction to survival prediction to classification and even clustering. And there are multiple streams of measurements usually available and giving rise to high-dimensional problems. And the temporal pattern are usually a mixture of smooth and rough changes and typically display some Markovian dynamics. So despite the progress we've made in time series analysis, this complex and diverse challenge means that we still need to continuously improve and innovate. So in today's talk, we'll be mainly talking about two primary goals. And the first goal is to forecast individual level disease trajectories. And this relates to the goal of dynamic forecast. How will patients' observable health status change in the future? What will happen next? And the second and related goal is about estimating individual level treatment effect over time. So it's related to the first goal, but now we care about really the treatment and how the disease trajectory will change in response to different treatment regimes. So let's first talk about the dynamic forecast. Essentially, we would like to build prediction models to better understand and predict disease progression using the available EHR data. So in the training time, the method learns model parameters from the available EHR data. And in the test or runtime, it issues dynamic forecasts for the patients at hand. And this type of model can not only be used for clinical decision support, but also unravel new understandings of disease progression, both on the personalized level, but also on subgroup and population levels. And our lab has made many contributions in this area, and please see our website for a more comprehensive introduction on the basics. And especially we offer a comprehensive view on how dynamic forecast is related and interplay with other research topics. But one common challenge when it comes to healthcare data, especially EHR data, is that the observations are made irregularly and sporadically. So if we think about a patient, we can only observe a patient when the patient visits a clinic. So the time between consecutive clinical visits might be quite random and maybe quite irregular. And this poses a challenge for the more traditional deep learning methods, such as the family of recurrent neural network methods. And this includes popular models in like LSTM, GRU, and vanilla RNN. So these models are designed to operate in discrete time, and it can only handle regular observations. And the fundamental cause is that the internal state of an RNN is only updated at regular intervals. And this means that the states are constant, the latent states are constant between two observations, which is not what we would expect when the disease are progressing in continuous time. So realizing this limitation, researchers have developed new architectures to fix this limitation. And examples include attentive state space model, GRU-D, and phase LSTM, among others. And this model employs a temporal decay function to model the change of states between two observations. And this means that the latent states are no longer constant functions. And it somewhat addresses the problem. However, the functional form of the temporal decay function is usually pre-specified and often involve a fair amount of handcrafting. Usually, in some model, a simple exponential decay is used, and very often it does not really capture the complexity of real disease dynamics. Hence, more recently, a new class of deep learning models come into being, and these are especially capable of tackling irregularly made observations. And these are neural differential equations pioneered by the neural ODE model. And they can enable continuous time model by design, and it essentially models a differential equation. And this type of model opens up a viable way to leverage existing results from differential equation literature and enables us to analyze the property of the method and design better training regime and loss functions. Apart from the deep learning method, there are also non-deep learning approaches. For example, the Gaussian process, semi-Markov model, and functional representation methods. However, these methods also have their own issues. For example, handle high-dimensional variables and inferring latent variables. And our lab has also made contributions in this work, in these fields. And today we'll be introducing our most recent work that essentially marries the neural differential equation framework and the functional representation framework, and this is Neural Laplace. So before going into detail, I'll briefly talk about the neural differential equations. As we all know, differential equations are equations that involve derivatives. They are commonly used in science to describe continuous time dynamical systems by modeling the change in infinite small time, essentially the time derivative. There are many classes of differential equations, ordinary differential equations, stochastic differential equations, control differential equations, delay differential equations, integral differential equations, and many more. And there are rich mathematical theory and related fields such as control theory. So it is neural ODE is a very good example to illustrate what neural differential equation does. So it assumes a data set of points x1 collected xi and ti. And neural ODE models the derivative of the change of x in terms of t, and parameterize this derivative with a neural network. And the key contribution is that the neural ODE is able to train by solving adjoint sensitivity gradients and allows efficient backpropagation. And neural differential equation models is really a proven method in it has really achieved fantastic results in irregular sample time series and its current state-of-the-art methods on many healthcare benchmark data sets. However, as I alluded to, there are actually many different types of differential equations, from ordinary to more complex ones. And it is still an open question how to design a single model to capture many of them. So Neural Laplace is essentially our solution to that. And it can model a broad range of differential equations by modeling the solution in Laplace domain. And with that, I will hand over to Sam, who will give more detail on Neural Laplace. Thank you.
You can see my screen okay?
Yeah, looks great.
Yep, great. Yep. So hi, I'm Samuel Holt, and this is Neural Laplace, learning diverse classes of differential equations in the Laplace domain. This is joint work with my excellent co-author Zhaozhi Qian, who we just heard from, and my supervisor Mahela van der Schaar. So to build on what Zhaozhi just very excellently introduced, learning differential equations that govern dynamical systems is of great practical interest in natural and social sciences. The pioneering work of Qian et al. In 2018 introduced the neural ordinary differential equation, which can model temporal states according to an ODE, where the function f is unknown a priori and is learned by a neural network. However, there exists much broader classes of differential equations for which neural ODE cannot model or describe. These differential equations are formulated to capture more temporal dynamics, which are beyond an ODE's modeling capacity. Prior works have attempted to address these limitations separately and individually, which leads to a suite of methods that are often incompatible with each other. Whilst there has been some work in adapting neural ODE to model delayed differential equations specifically, their specialized architecture and inference methods rule out the possibility to model other classes of differential equations, for example, integral differential equations or force differential equations. Similarly, the work on modeling stiff ODEs have proposed alternative system parameterizations that are invalid for other classes of differential equations, as we see here. In this work, we take a holistic approach and propose a unified framework, Neural Laplace, to learn a broad range of differential equations that have vast applications. Importantly, Neural Laplace does not require the user to specify the class of differential equation a priori, that is using between an ordinary differential equation or a delayed differential equation. Rather, with the same network, the appropriate class of differential equation will be determined implicitly in a data-driven way. This significantly extends the flexibility and modeling capability of the existing works. Relevant and applicable to many healthcare and medical problems, we see broad ranges of differential equation types, such as delayed differential equations as Ph.D. models, integral differential equations as epidemic models, forced ODEs in medical oscillation techniques, and also stiff ODEs are quite common in healthcare analytics. Unlike existing works, Neural ODE, which solve the ordinary differential equation in the time domain as illustrated here, Neural Laplace leverages the Laplace transform and models the differential equation in the Laplace domain. This brings two immediate advantages. First, many classes of differential equations, including delayed differential equation and integral differential equation, can be easily represented and solved in a Laplace domain. Secondly, Neural Laplace bypasses numerical ODE solver and constructs a time solution xt with global summations of complex exponentials through the inverse Laplace transform. It is worth highlighting that the conventional Laplace transform method is used to solve a known differential equation with an analytical form, yet Neural Laplace focuses on learning an unknown differential equation with neural networks and leverages the Laplace transform as a component. As we see here in this illustration, however, modeling with a neural network, a mapping that can map from 0 to infinity, is inherently difficult. Therefore, we leverage the Riemann stereographic projection, which is the trick that makes this work possible, to learn a representation of the stereographic projection sphere instead to model Laplace representation. The Neural Laplace architecture involves three main components: an encoder that learns to infer and represent the initial condition of the trajectory, a Laplace representation network that learns to represent the solutions of differential equations in the Laplace domain, labeled 2, and labeled 3, an inverse Laplace transform algorithm that converts the Laplace representation back to the time domain, with the block diagram shown here. We now discuss each component in turn. We need to infer the initial appropriate condition, which implicitly determines the class of differential equation. To achieve this goal, Neural Laplace uses an encoder network to learn a representation of the initial condition. We highlight that the observations can be encoded at irregular times. The vector P is learned through initial condition representation of dimension K, and the encoder H has trendable weights gamma. Neural Laplace is agnostic to the exact choice of encoder architecture. In our experiments, we use a reverse time-gated recurrent unit, and other recurrent neural network encoder methods can be used. Given the initial condition representation P, we need to learn a function L that models the Laplace representation of the differential equation solution. However, the Laplace representation Fs involves singularities, which are inherently difficult for neural networks to approximate or represent. Therefore, we instead propose to use a stereographic projection of the Riemann sphere to translate any complex number S into a coordinate on the Riemann sphere, into a closed compact set, as we can see here. The improved smoothness with the singularity mapping is shown in the illustration and geometry in the above figure. A nice example of this map is the function 1 over S, which corresponds to a rotation of the Riemann sphere 180 degrees about the real axis. With the stereographic projection, we introduce a feed-forward neural network, G, to learn the Laplace representation of the differential equation solution. After obtaining the Laplace representation Fs, we can compute predicted or reconstructed state values using the inverse Laplace transform algorithm. We highlight that we can evaluate xt at any time point t, as the Laplace representation is independent of time once learnt. In practice, we use the well-known inverse Laplace transform Fourier series inverse algorithm, which can obtain the most general time solutions whilst remaining numerically stable. To test whether the models are able to accurately uncover the temporal dynamics, we evaluate their accuracy in predicting the future states of the system, that is a root mean squared error. We split each sample trajectory into two equal parts, 0 to 10 and 10 to 20 seconds, encoding the first half and predicting the second half. For each data set, we sample 1,000 trajectories sampled from a different initial condition, giving rise to a unique trajectory defined by the same differential equation system. For example, two trajectories of the Mackey-Glass delayed differential equation offer insight into the model's ability to capture long-range dependencies. The trajectories have the same recent history, but different distant histories, and evolve very differently into the future. Hence, successful extrapolation requires the model to keep memory of the distant past, which Neural Laplace is able to do and outperforms the benchmarks. Neural Laplace achieves low root mean squared error, extrapolation test error on all different differential equation datasets analyzed, such as delayed differential equations, stiff differential equations, forced differential equations, and integral differential equations. Specifically on the stiff van der Pol differential equation, Neural Laplace can be correctly extrapolate the differential equation dynamics. That is, it can model the periodic stiff solution, capturing the discontinuities of the derivative solution and the periodicity, whereas neuro-ODE, augmented neuro-ODE, and latent ODE methods correctly capture the periodicity, however fall short in modeling the derivative discontinuities as they enforce overly smooth solutions. neural flow methods suffer from similar smoothness behavior. As Neural Laplace can predict any future time with one pass through the network, this translates to order of magnitude faster computation time compared to numerical stepwise ODE solver methods, with similar computation time to other integral methods. In conclusion, Neural Laplace can learn diverse classes of differential equations by modeling in the Laplace domain. It can reconstruct any trajectory xt at any time t. It scales linearly with the number of time points to evaluate, whilst modeling diverse classes of differential equation systems better than existing methods. We've also released a PyTorch implementation of Neural Laplace, including GPU implementations of several popular inverse Laplace transform algorithms. The code for this is available at GitHub, Sam Holt, Neural Laplace. We also show a few code examples, and it's very simple to use, and you can try it out right now. For example, we can learn a differential equation representation for a delayed differential equation system that of a Locata-Volterra system with delay. Or we can also learn differential equation representations to extrapolate a sawtooth 1D waveform as well. We hope this work provides a practical framework to learn a Laplace representation of system, which is immensely useful and popular in the fields of science and engineering.
With that, I would like to introduce briefly our next speaker, Nabeel Seedat, who is also a first-year PhD student in our lab, like Sam. And Nabeel will be speaking about modeling counterfactual outcomes with neural differential equations. Nabeel, if you would like to share your screen now and start your presentation.
Okay, perfect. Is everyone able to see my screen?
Yep, that looks great.
Okay, so hi, good afternoon, everyone. My name is Nabeel Seedat, and I'll be talking about continuous time modeling of counterfactual outcomes using neural controlled differential equations. And this is joint work with Fergus Emery and our co-authors, Alexis Bello, Zhaozhi Qian, and Mihaela. So imagine that we actually have some sort of lung cancer patient that we observe over time. We observe their actual values and covariates over time, as well as certain treatments up to some time point t. At this point time t, we actually want to understand what would happen to this patient at a future time point and under future treatment plans. And more specifically, we want to estimate counterfactual outcomes for this individual given their history under a sequence of future treatments. And these treatments could either be no treatment at all or any arbitrary type of treatment plan in the future. And understanding and modeling this problem is fundamentally important for a variety of reasons in healthcare, of whether a clinician should treat the patient in the future, how they should treat them, and additionally, when they should treat them. And actually, estimating counterfactual outcomes as accurately as possible in this case allows us to answer these three what-if questions. However, existing works are very much limited to fixed regular time intervals between observations and have largely used discrete time methods. However, in reality, clinical observations and in many other areas, observations are often not at regular intervals. And the reason is patients' age do not come in at regular intervals. And in addition, treatments are often not administered at these regular intervals. Rather, both patient history and future treatment plans are often observed irregularly up to time t. And therefore, we ask the question of how can we learn from such irregular observations, and how can we address this issue of irregular sampling when we want to estimate counterfactual outcomes? And our proposed method for this is the treatment effect neural controlled differential equation, otherwise called TE-CDE. And the key idea is to learn a continuous latent representation of the patient's state as a solution to a controlled differential equation. At this point here, I do want to take a brief segue from TE-CDE and briefly describe the difference of how did we actually leverage the advances in neural CDEs, and what is the fundamental difference of a CDE compared to an ODE and an RNN. So as you can see on the right, we typically have an RNN, which is often applied to discrete time modeling situations, and we see the evolution of the hidden state only evolves at each observation point, and we see an update of the hidden state at that time. And ODE, on the other hand, does have evolution between observation points. However, largely the system dynamics are governed by an initial value condition. In a neural CDE, on the other hand, where it's a controlled differential equation, the controlled nature comes into the fact that we are able to update the system dynamics on the basis of the observations that we are seeing, i.e. that these observations control and change the underlying dynamics in which we learn. In this case here, we determine that the patient's latent trajectory evolves by some controlled differential equation, and we aim to model this in TE-CDE, which you can see in the equation below. So now back to TE-CDE. The key idea, once again, to reiterate, is to learn a continuous latent representation of the patient's state as a solution to a controlled differential equation. Of course, we don't know the underlying controlled differential equation, and we use neural networks to solve this underlying problem. So in TE-CDE, we have two components where we have an encoder and a decoder architecture. We first take the patient's observed covariates and observed treatments up to time t, and we encode them into a continuous latent path z. This continuous latent path z then evolves as a solution to a controlled differential equation. After time t, when we want to decode and predict the counterfactual outcome, we then update this latent path using an additional CDE, which we can then use to decode and predict the counterfactual outcome at a variety of time points, whether it's T1, T2, or T3. An additional challenge, though, that's very different from pure time series modeling that we find in counterfactual estimation is that of time-dependent confounding. And by this, we mean that previous treatments and observations at previous time points might bias our future observations. And this is time-dependent confounding. And we address this via domain adversarial training in our architecture. However, we need to now take TE-CDE and assess how does it actually work. And in real life, of course, it's not possible to observe counterfactuals, and therefore we need some sort of simulation environment in order to benchmark TE-CDE and compare performance. And for this year, we use the well-known lung cancer tumor growth model of Geng et al., which models the change of tumor growth with the effects of chemotherapy and radiotherapy on the actual tumor growth. And this serves as our underlying system dynamics. Now we move on to this idea of how do we actually model irregularly sampled data that I've talked about quite early, which is quite common in healthcare. And for this, we introduce a flexible observation process, which we parameterize by a Hawkes process. And it has two interesting components that we'd like to highlight. The first is that it's self-exciting. And by this, we mean that once we've seen an observation, we're more likely to see observations much more frequently in the future. Additionally, it is state dependent. And by this, we mean we base the states of this observation process on the American Joint Council for Cancer stages, where patients who are more severe and have higher cancer stages are going to be observed at more regular intervals and observed much more often, compared to patients who have much lower cancer stages and are less sick and are more likely in a clinical setting to be observed less frequently because of their reduced severity of state. And this observation process serves to create this irregularly sampled setup that we wish to now test models on. So in terms of our experimental results, we show that TE-CDE outperforms state-of-the-art discrete time baselines, both CRN and RMSN. We demonstrate the importance of domain adversarial training, particularly for high values of time-dependent confounding. And we show utility not just for counterfactual estimation, but also for predicting treatment accuracy at varying levels of time-dependent confounding. The contributions of this paper is that we obviously extend counterfactual estimation from the conventional regular time setting, and we bring it to irregular sample setting using the mathematics of controlled differential equations. We introduce a novel simulation environment so that we can test out these irregularly sampled observations, and we propose TE-CDE as a solution within the setup, modeling for the first time a patient's latent trajectory as a solution to its CDE. And finally, we demonstrate utility of our approach both for counterfactual estimation and for treatment accuracy. Thank you.
So with that, I would like to move now to our panel discussion. And I'm delighted to be able to introduce our two guests today. And these are Dr. Emma Slade and Dr. Javier Hernández. Emma is a senior AI ML engineer at GSK, and Javier is the principal researcher at Microsoft Research in Cambridge. The discussion with our two panelists will be chaired by Mihaela. And if you have any questions for either of our panelists, or in addition, any of the other speakers today, do continue to post them in the Slack channel, and we'll open up the Q&A after a few questions to our panelists. So Mihaela, I'd like to pass over to you for the first questions, which I think are for Javier.
Thank you very much, Fergus. But first, I'd like to thank very much to both Emma and Javier for taking the time to join us today. And of course, all our participants in Inspiration Exchange, thank you for being here. So Javier, I'm going to start with a question to you. In which settings and applications do you think that these neural differential equations will be especially useful? And to follow up, are there specific settings or applications where the neural differential equations may provide specific benefits compared to standard deep learning?
First of all, thank you very much for inviting me to be part of this session and this panel. It's a pleasure to be here, being part of these amazing sessions. So thanks for your question. So let me give you my opinion from the high level, and then coming to the details. So I'm a fan of semi-mechanistic models, and models in which we can combine data-driven approaches with models in which we have some prior information that we embed in our models, and how to combine these two things is key, in my opinion, to solve most of the real-world applications, and particularly in healthcare. So I see neural ODE models as a playground for doing that in a very nice way, and I particularly like the combination of having data that evolves in time, that are observation from dynamical systems, some prior information that we may have about the dynamical system in the form of some ODE models, and how you can connect that with some causal implications, as well as we have seen in some of the talks, in terms of the mechanism that you are imposing the model that you are learning from data. So I think cases where you have that are a very nice playground for this type of model to have an impact. And I can think of two specific applications, for instance. So in a pharmacokinetics model, for instance, where you want to analyze the effect of dose in the response of patients to a drug, you know a lot of that. And I think the interesting discussion there to have is how do you embed the knowledge that you have about a specific problem, about a particular molecule, in the response that you will have when that particular compound is given to a patient. And obviously you will have the problems that have been already discussed, like you have regular time points. I think you will have problems like you won't have a lot of data probably to train this model, which will cause some issues, because you will have to train the ODE. So that's a place where I think this model will be very useful. And the other scenario that comes to my mind is problems in biology where we want to study the dynamics of the cell. So in the past, I did some work on latest form models in which we have some gene regulatory network that we can model by a differential equation. So we can inject some intervention in the cell because we can expose the cell to certain conditions and to see how that propagates through the system. I think that can give another nice playground or application where these models could be useful. So I see those couple of applications like a potential use cases for this.
Javier, this is a little bit unplanned, but based on your answer, ourselves, together with Zhaozhi, who presented the first tutorial, we did some early work last year combining pharmacological models, PK/PD models for dexamethasone with data. So trying to correct model misspecification of PK/PD models using data. And also, like you say, trying to bridge the lab, in this case, the pharmacological model and the clinic. are there settings where you think that indeed we would prefer to learn directly from data as opposed to maybe bringing these inductive biases from pharmacology?
That's very interesting. I guess it depends on the application, because in many of these problems, so neural ODEs are very good and very flexible when we want to do predictions beyond the time where we have done an intervention. But in many of these problems, we are not really interested on making predictions beyond an intervention. We are more interested on understanding the dynamics of the system. And in those cases, we may think that, well, if I can work with a less flexible but better specified model, in the sense that I have an ODE that depends on some parameters, I can think about, well, I'm going to do maximum likelihood estimation for those parameters of the ODE, and then I have some very clear and clean interpretation of some dynamics of the system. So cases in which we want to go fully data-driven, I'm not sure. I suppose cases where we really want to make sure about having good predictions without worrying about interpretation, that would be cases, but I cannot think of one specifically from the top of my mind now.
Thank you. Fergus, the new question for me, can you please display it? So the second question is for you, Emma. What areas do you think neural differential equations might have significant impact? And this with a view of you both as a former physicist, but also as your work in biology more recently. And how do you envision this neural differential equation being used in the real world, especially in healthcare and biology, but of course, also in physics?
Yeah, so I think in healthcare, one area where this would probably be quite an important methodology to be used is in directly using electronic health records for things like building data-driven clinical decision support tools. So the problem with using EHRs is because they have huge amounts of missing information. We have a regular sampling of patients. We have multiple measurements, different kinds of measurements on the same patient. We have kind of multi-omics type data of them. These are all things that using neural ODEs can alleviate the issues and be able to actually model all this kind of information without relying on too many assumptions from just using regular ODEs or regular differential equations rather. The problem is then obviously, as I think Nabeel was saying, with all these counterfactuals that come along with having these irregularly sampled data and these very kind of noisy data, but there is no reason to think that further development of neural differential equations won't allow you to make quite strong predictions on patient outcomes. And in particular, stratification of patient populations is something that's been shown to be quite good using neural differential equations. And that is not something that's the problem with a clinical decision support tool is, you're kind of saying, I can make a prediction as good as a doctor. If you're saying I can build a tool that can help make decisions such as stratifying patient populations so you can decide what kind of drug or what amount of drug to give a patient, these are things that just enable clinicians to make their kinds of decisions. That's obviously on the biological side, the healthcare side. On the physics side, I think, yeah, it all comes back down to being able to model dynamical systems, and particularly if you've got things like harsh kind of discontinuities in your time dependence. So you've got something like a discrete and a continuous time modeling that you're kind of trying to jump between. So like you've got discrete and continuous phase spaces and this kind of stuff. Again, you can use neural differential equations in these domains where normally you can't really have a smooth transition between your continuous time modeling and your discrete time modeling. And this is something that I think, although going back to biology, if you're trying to model fMRI imaging, I think work has been done using neural ODEs to do this, because you've got these two distinct kind of phase spaces that you can use neural ODEs to model quite nicely.
Thank you, Emma. You are alluding in the first part of your answer to almost like a temporal clustering using these ideas. Am I right?
Yeah. So you can use the historical data of patients to stratify future predictions on how their disease might develop or how their response to a drug might develop. So again, this can integrate in with PK/PD modeling, right? If you're trying to model the intensity of a drug response over time, along with stratifying patient populations and their response on a much more holistic scale of the actual patient rather than the response of a cell to a drug, for example.
I'm now going to surprise one of my own students because I'm going to use your question as a surprise to him. He doesn't know yet that this question is coming, but we have done quite some work in the lab on what we call temporal phenotyping or temporal clustering. But it was not based on neural ODEs. So your idea triggers new ideas, at least in my head. Zhaozhi, sorry for putting you on the spot. Do you see any advantages maybe to do temporal phenotyping or temporal clustering like Emma was mentioning, but then with these new ideas of neural Laplace or neural ODEs? Sorry to throw it at you, but
because I think in the previous incarnation of temporal phenotyping, I think we're still not handling irregular sampling as good as we can nowadays. I think it will be good to kind of revisit the idea and using some of the new methodology developed over the last few years and think can we even achieve better performance on that front. Yeah.
And maybe look at states and stability, like Sam was saying, and see if that plays a role in the clustering. Apologies, Fergus. Let's go to the next question. But our guests are putting me to think out of the box. Are there any methods for using neural differential equations from you, your organization, or anything else that you can point us which you found interesting and useful and you would like to bring to our inspiration exchange community?
I can mention something. So last summer we had an intern who was working on neural ODEs, and we were looking at the problem of generating counterfactuals, very similar to the second talk. But something that we focus on that I think is key to use these methods in practice is we focus on quantifying the uncertainty of the predictions and quantifying the uncertainty of the counterfactuals, so that we can think about having a neural ODE where we model the function f with some neural networks, but now we can think about model that with some Bayesian neural network where we have some prior over the parameters. The beauty of that is when we think about that, the neural ODE transforms in some stochastic neural ODE for which you can study the properties, and now you can generate predictions and counterfactuals with uncertainty quantification, which is something that is key for decision making and for making more informed decisions if we want this to be used by clinicians or to inform clinical decision making. So this is something that we did with Stephanie Halland and Edward De Bruyck, who was an intern last summer. We published it in AI Stats, and I think it's a very interesting direction that brings together the semi-mechanistic type of approaches that I was mentioning before with uncertainty quantification. And obviously, I guess one can take that further if you want to think about the science based on time series, or when do you need to collect data that will maximize the information flow that you have in a system, or examples like that.
Yeah, we have seen the excellent work. Emma, anything else to add, or shall I go to the next question?
Well, I think it's quite funny. So the main, I think, limitation of using neural ODEs in the healthcare domain is because we have irregularly sampled data most of the time. It's difficult to use normal ones. So I'm not trying to kind of, because it's your lab and your group who've done this work, but the recent work on being able to do this continuous modeling despite the irregularly sampled data kind of opens up the opportunity to actually use this with actual healthcare data rather than in a more theoretical academic setting. You know, prior to that, it was just something that was a nice method that definitely had the potential for use in healthcare. But until methods were developed that could deal with the irregular sample data, it was something that very much was just a theoretical construct. So it's like, now potentially yes is the answer.
Thank you so much, Emma. Fergus, the last questions. Do you see any key limitations preventing more widespread adoption of neural differential equations?
I think my answer is
Emma,
kind of the same.
I'll start with you, Emma, yes.
Yeah, I think my answer kind of is the same from the healthcare point of view. It's all about this fact that the data we get is really inconsistent. There's huge amounts of missing data. Patients don't often sometimes patients don't turn up for them blood test or whatever, and that block in the table is empty, and it's very difficult to model that normally. So my answer is kind of my previous answer of the main limitations are consistent general methods that can deal with this. So we know we have one method that we can show with the controlled differential equations can deal with this irregular data. We need general methods to be able to deal with this kind of irregular sample data.
Yeah.
Thank you so very much.
I completely agree with Emma, of course. Something I was thinking, I think this links with my previous points as well, is the idea of the interpretability of a neural ODE, which is something that we lack a bit. So when we think about autoregressive process, right? So I have a time series and I model the time series with an autoregressive process. I have a parameter that I know how to interpret, right? That relates the past to the future, and I know what that means. When I model a time series with a system of differential equations with some parameters, I know very well about the dynamics and I can interpret those parameters. What can I do with a neural ODE? It's something I can say about how am I making the predictions of what is causing that the patient is evolving in a certain way. So I think there is some work that could be done there to try to open a bit the box in these models. And I think that will increase adoption if there is something that we can say about that.
Food for thought for our entire community. Thank you so much, Emma and Javier. Fergus, I'm returning to you with questions now from the audience.
Great, thank you, Mihaela, and thank you also, Emma and Javier. Much food for thought for myself. My brain is now on fire from all of these different possible directions and thoughts. So we've had quite a few questions in the Slack channel. So I will start going through those. And apologies if we don't get through all of them in the time we've got remaining. There's definitely some overlap between questions, so I'm going to try and kind of combine a couple of questions where necessary.
Yes, so neural differential equation, yeah, it's very interesting, but I'm kind of confused by like how is it different from like a physics informed neural network? Because I see neural differential equation, if we have prior knowledge, like in the form of ODE or Ph.D. or whatever, we are trying to encode the knowledge, right, prior knowledge into neural network. I know physics informed neural network is already doing that. So I want to know what's the difference and what's the advantage of neural differential equations. Yeah.
Sam, Zhaozhi?
Yeah, maybe I can take that one. So I think so these are really quite two related topics, but they come from two different angles. So in my view, the physics informed neural network is using some of the physical principles as inductive bias to design neural network architecture. So one concrete example is all these variants of Hamiltonian neural network, which essentially build on top of this principle of preservation of energy and stability and many good properties. So from that aspect, it's kind of addressing some of the different problem. It can be applied for also applied in neural ODE framework. So the vanilla neural ODE does not have any physical informed constraints built in. It's just a kind of people use residual networks or fully connected networks. But with the physics informed aspects, it provides kind of even a new way to design the architecture or some training mechanisms, and it applies also to neural differential equations.
Thanks, Zhaozhi. The next two questions I'll ask both of you to unmute are on generation using these methods. So Jiang, Yulun, and Garang, if you could both maybe unmute and ask your questions, and then I'll ask Zhaozhi to take these questions kind of together.
Thank you. Can you hear me? So I'm
Yeah, we can hear you.
so I'm a student doing an internship in the company with the project of synthesizing mathematical time series. So the most difficulties in my project is the irregular sampling and the irregular treatment to the patient. So I'm wondering whether new ODE can solve this problem. Thank you.
Yeah, I think your ODE is a very good, strong candidate that you should be thinking about. So your ODE essentially, when we train your ODE, it can be trained on the irregularly observed samples. And after the model is trained, you can also use it to generate new time series data. You only need to kind of infer the initial condition. So given the initial condition, essentially the whole kind of trajectory becomes a deterministic curve, and you can obtain it by solving the initial value problem. So, but probably in order to make it truly a generative model, you need to kind of infer the distribution of the initial condition so as to be able to sampling from this initial condition distribution. Yeah.
Thanks, Zhaozhi.
Thank you.
Garang, maybe we take your question next. If you are you still here? Perhaps not. Maybe I will.
You can read it. Maybe you can read it, Fergus. Then sorry for that.
So this question is: Can a regular time series in healthcare be modeled using a language modeling approach, e.g., next word prediction? For example, while forecasting EHR data, which has irregular time steps, we may be only interested in how the sequence is trending, and the temporal information from the exact timestamps of the observations may not add value. I think a couple of people like this question, so I think it's important we try and take it. I'm not sure, Sam or Zhaozhi, if either of you want to take this, or maybe even one of our two guests want to take this, because I think this is quite a general question, not specific to something, any of the specific methods mentioned.
If nobody answers, Zhaozhi, we throw it at the most senior among the students. We don't let the first-year students answer complex questions like this one.
Yeah, I think that's a very interesting way of looking at it. So I think essentially the question is, what will happen if we ignore all the temporal information, just treating everything as a language model? And I think this is kind of the baseline that everyone compares against, or essentially part of the baseline that everyone compares against. So of course, the simplest thing you can do is to completely ignore the timing. However, in healthcare, I think there are plenty of evidence that the timing, the duration, and even the informative sampling is playing a quite significant role in understanding and modeling disease trajectory. So personally, I think the timing is indeed very important, but how to encode this timing it's another story, right? And also, you bring up the topic about language models and obtaining some learning from natural language modeling. I think this is also a very interesting idea. Maybe we can think about some way to import some best practices from natural language processing there. But I think this is interesting area to be explored in the future. Yeah.
I think in a way, in my mind, it's like somewhat the kind of counter arguments. One is, can you neglect the time dependence in the data and healthcare data? And the answer is pretty much never. There's no kind of Markovianness to the data. It's hugely dependent on the history of the patient sampling. And on the other hand, could you use something like a transformer-based model in order to be able to capture much more of the patient's history? So go to the other extreme of try and capture huge amounts of history about the patient data. So in a way it's like, can you use sequence modeling to either neglect the history or use all of the history of the patient's data?
Emma, I'm going to jump in here because this is exactly what we tried to do with the former PhD student in the lab, Ahmed Allah. We have a paper of 3 years ago called Attentive State Space Models, where we put attention on the states and they are dependent on the irregularity of the observations. And we try to learn from data whether how important is the past, and how long ago in the past should one go when making this forecast of the future. And we integrate to be able to do that ideas from statistics, from Markov models, hidden Markov models, with ideas from recurrent neural networks. So maybe not neural ODEs, but maybe attentive state space models. Sorry to jump.
No, that's great. Thank you, Zhaozhi. Javier, do you want to add something to that?
No. I was going to say that's really cool. And I guess the question is how do you model the context that you want to use when making the predictions, right? And how do you capture that? And how do you find time and encode it in the model? That's interesting.
Fantastic. I think we're going to change pace. I think we've got time for maybe one more question. And I'm going to change pace and maybe ask it of Nabeel and Toon. Do you want to unmute yourself and ask your question? I think it was on the TE-CDE work.
Yeah, thank you, everyone. This is indeed a question for Nabeel. I was wondering, so you make a technique that can take irregular samples as input, which is really valuable, I think. And it also has really good performance in the experiments. I wondered how you compared your technique to existing techniques that couldn't take irregular samples as an input. So for example, CRN, how did you adapt that to also take irregular samples as an input?
Thanks for the question. So I think that is a super valid question. So typically, I guess most people, what they do when you think of having missing observations and you want, say, the RNN always to have some value to be able to make a prediction, you typically impute that missing value. So that's the approach that we went with when comparing these discrete time methods where maybe we didn't have an observation there and we wanted to still make the prediction at that point. So we simply just imputed for all of those methods as a way to somewhat make a baseline comparison.
No, I will add that I've definitely seen other works using things like recurrent neural networks where you just kind of ignore the irregularity and you just say, okay, let's just assume these are regularly sampled even if they're not. And that is definitely an even weaker baseline. So this kind of interpolation and imputation approach is a bit stronger than that. But I'm sure there's other ways of adapting these models out in the literature there as well, beyond just these two approaches. I think we're already now a couple of minutes over. So with that, I think I will start to wrap up for today's session. And thank you everybody who raised questions. And apologies that we didn't have enough time to cover them all. We will try for some of the questions to answer them in the Slack channel after the session. So if you did ask a question, please do check back there maybe in a day or so, and we'll see if we can have answered those. Very briefly, I wanted to highlight again that what I did at the start. The lab is recruiting the PhD students, so please do apply via our website and join us for our meet and greet. We'll send out more details in the future about that session. And finally, I just want to thank all of our presenters and our guests, Javier and Emma, for joining us today, and say that the next Inspiration Exchange session will be on October the 25th, where we'll be discussing frontiers in interpretability. And with that, say thank you very much, everybody, and enjoy the rest of your days, and see you soon. Thank you.